Hey everybody, Dr. Duncan here with our third video on the paper by Dowdy and Connor, Nonchalant Flight in Tiger Moths is correlated with unpalatability. In this video, we're going to cover essential results and the discussion points of the paper. So one thing I want you to understand about this study is that the data they collected is what's known as binary data. Examples of binary data include the results of flipping a coin. You either get heads or you get tails. Another example of binary data would be classifying organisms as whether they're male or female, or perhaps dead or alive. All these outcomes, there's just two outcomes. Now, most of the statistics that you're familiar with do not work very well with binary data. That means no t-tests, no ANOVAs, and no regressions. Those tests are in general made for data that conform to a normal frequency distribution as depicted here. But the results from this paper are definitely not like this. There's only two categories of outcomes, so our researchers have to use a special family of statistics that can work well with binary data. All right, much of the data that the authors produced is summarized here in Table 1 and Table 2. Did you struggle to understand it? Me too. As it turns out, these data are not super important to our understanding of the main results. So but basically what's behind here these numbers are the calculated likelihoods of particular outcomes. Outcomes such as the bat rejects the food or it eats the food, or the moth evades the bat or the moth doesn't evade the bat. This is all part of that special family of statistics I explained is related to binary data analysis. So let's go ahead and move on then to the main results from these trials, which is represented here in Figure 1. I've blocked out the bottom panel of Figure 1 so that we can focus here at the top. All right, let's take a look at what we got going on here. As always with a new chart, let's take a look at the axes first. And what we'll see here is on the x-axis, we've got our 5 species of tiger moths. On our y-axis, our vertical axis over here, highlighted with the green marker, you see that we are measuring the percentage of moths that exhibit nonchalant flight behavior. So this is from the arena trials. And what you see within each of the bars, the black and the gray represent whether or not the moths exhibited nonchalant flight. If they did exhibit nonchalant flight, that's represented by the black here. If they did not, that's represented by the gray here. Over here on the right, they've got it labeled as true or false. Think of it as them asking the question, did the moth exhibit nonchalant flight? True or false? That's your binary data, by the way. Okay, the next thing I want you to notice is that they have inscribed on these bars some more information about their findings, their results here in the white text. The top number is the sample size. So in this case, there were 97 individuals of this species that were tested in the arena trials. And then the bottom number, which is a percentage, is simply making it easier for us to read the y-axis. It says that 23% of this species, only 23% of this species exhibited nonchalant flight. Okay, now that we understand what this graph is showing us, let's talk about the meaning. And what you probably have already noticed is that these species are arranged such that we go from species that show the least amount of nonchalant flight on the left to those species that show the most amount of nonchalant flight at the right. Please forgive my very stupid looking arrows that look like some sort of weird palm tree. All right. The authors, of course, chose to arrange the moths in this order so that visually we have a nice increased chance of the moths exhibiting nonchalant flight. Of course, when you are a researcher and you're getting your data, and it comes out piecemeal, you don't necessarily see it in this nice clean pattern. This is all done after the fact to make it more easy for us to see the patterns involved here. The bottom line from this part of the study is that different species of moths show different levels of nonchalant flight. That was essential for this study to work, because of course they're trying to compare nonchalant flight variation across species with palatability across species. Okay, given all that, let's now look at palatability. This is also figure 1, and this time I've blocked out the top panel. And what I'm showing you here is the data from the palatability trials. Once again, we have our species arranged here on the x-axis in the same order that we had in the top panel. And we've got percentage of moths that were classified as being unpalatable on the y-axis. The numbers here again represent sample size and our outcomes. So in this case, for this species of moth, 19 of those moths were determined to be palatable to the unpalatable to the bats. And this, just because I kind of fumbled my words there, let me give you another example. In this species, 33% of the moths were determined to be unpalatable to the bats. The white numbers and with the gray in the background, the top number there, those represent our sample sizes. So that's the numbers of these moths that were fed to the captive bats in those trials. Once again, you see that as the species are arranged here in this order, we see that there's in general an increase in unpalatability across these 5 species. Now, you already remember from the previous slide that the species in that same order showed a very similar pattern. Let me get all that set up so we can see it all at once now. Okay, here we go. We have both panels visible at the same time, and the authors have some very clean results in that with the same order of species on the x-axis for both panels, both of the top panel and the bottom panel are showing an increase in the outcomes, whether it's nonchalant flight or unpalatability. Now, within each of these panels, they also did some statistical tests to compare the species to one another. So let's take a look at that. So you might have already noticed that at the top of each of these bars, there's a series of letters. I'm kind of pointing to them up here with my green arrow here. The letters, you might have seen this before in the results of ANOVA statistical results, where you have multiple categories and you're comparing them to see if there's statistical differences. And the same thing is happening here. Excuse me, not COVID. Each of these species that has a unique letter associated with them is statistically different from all of the other species. So let's take our first example up here at the top. This species, because it has the letter A here, and we do not see an A in any of these other categories, that means that this species was significantly different in terms of the outcomes here. They were significantly less likely to show nonchalant flight when compared to each of the 4 other species. Okay. Let's go through another example of that. So let's take species, the 5th species over here. This species, its outcome is represented by D, and you'll notice that the species to its left also has a D. Okay, that means that these 2 species were statistically similar in terms of whether or not they showed nonchalant flight. So they were equal to each other, okay? However, when you compare D to any of these other species over to the left, I'm sorry, you're not comparing D. When you compare this species over here, species number 5, I'm not going to try to pronounce all these scientific names. Oh, wait, that's our Cisthene martini. So when you compare Cisthenes martini to the other three species that are to the left of the panels, you see that they share different letters of the alphabet, indicating that Cisthene martini is significantly more likely to show nonchalant flight when compared to these three species over here. Okay. And just to teach a little bit more about statistics and how to read these graphs, you might have noticed that that a couple of these species are kind of interrelated in differences in some somewhat confusing ways. So D is so species 5 here is statistically similar to 4. Okay, species 4 here because they both share a D, but species 5 is statistically different from species 3. Even though both species 4 and species 3 share a C. Okay, that's not uncommon. So for these two species to be similar to one another, these two species to be similar to one another, but 5 and 3 are not similar to one another. That's a typical outcome in these kinds of comparisons, whether you're looking at ANOVAs or these special binary analyses, binary data analyses. Okay, let's get out of the weeds here for a moment now and then look at the big picture with regard to the study and its outcomes. What the researchers establish here with this figure is that there's variation across species in both whether or not they show nonchalant flight. We've got some significant differences there. And there's significant differences in the palatability of species. We have some that are much more palatable, like the one on the far left, and others that are much less palatable to bats, like the two that are on the far right, and then some that are at various levels in between. So that establishes the baseline fundamentals for being able to do the comparisons that they do. Now, you've already noticed, and we've already talked about, that in the way that they have these species arranged in this particular order, we see in general that, that the degree of unpalatability goes up and to the right across these bars, as does the degree of nonchalant flight up and to the right. And you might be thinking to yourself, and correctly so, wow, there seems to be a correlation there. But this particular display of the data isn't itself a correlation. This doesn't show us whether or not there's a significant rise in one variable as the other variable also rises. So for that, we need to turn to the next figure in the paper that we're going to focus on. Okay, this is figure 2 and table 3. They go together pretty tightly, so I've got them here on the same slide for us. And what I want you to notice is that we've got on the figure 2, we've got unpalatability, percent unpalatability on the x-axis, and we've got nonchalant flight on the y-axis. And of course, the authors chose to use the smallest font physically possible to print in a journal. I had to get my daughter to read it for me because I couldn't make it out. Okay. So what do we see here? We see that for species that have a high degree of unpalatability, they also show a high level of nonchalant flight. We also see that species that have a low level of unpalatability tend to have a low level of nonchalant flight, and species in between for both variables wind up in between, or in between for one variable wind up in between for the others. And when you graph it all out, you see that they have, in general, a very strong pattern of increasing unpalatability and nonchalant flight at the same time. So that shows some very strong support for their hypothesis that nonchalant flight behavior, sluggish behavior, is related to unpalatability and chemical defense. Now, I will point out a couple more things. This is getting into the weeds a little bit with the statistics, but this is how we learn more about statistics. These are the figure at the left is not your typical regression that you see in the typical papers that you've read up to now. Again, this is binary data, and with binary data, in this case, we're looking at the likelihoods of particular outcomes Remember, either bats are going to eat the moth or they're not in the palatability trials, or or the moths are going to evade the bat or they're not in the arena trials. And the outcome of this I've highlighted in yellow. The authors say that for a given level of unpalatability, nonchalance is expected to fall within these intervals with a 95% of cases. That's this gray zone that's around the graph here. This is showing that 95, based on the model that they've created from their data, 95% of the outcomes should fall within this gray zone, basically showing that still that unpalatability increases, as does nonchalant flight. And of course the line there, it represents the best fit line between those outcomes. Over to the right in table 3, we see some of the results of what's called a linear model of nonchalance from unpalatability. And I want to draw your attention to 2 points in this table that tell us the most information that's useful for our purposes. You might be familiar with regressions and how regression analyses give us an R-squared value. That R-squared value can be directly translated into the percentage of outcomes that are explained by the independent variable. Okay, in our case, the independent variable is unpalatability. And what we see is that their R-squared value, when adjusted for the design of the study, is at 0.87. That is really high. That means 80% of, well, let's read exactly here what the authors had to say. They said for every 1% increase in unpalatability, the likelihood of nonchalant flight is expected to increase by 0.66%. That's that value up here for unpalatability. And when you graph that out, you get the adjusted R-squared of 0.87%. A rough translation here, and don't hold me to this if any of you become statisticians, but a rough translation here is that unpalatability predicts 87% of the time, presents correctly whether the moths will do nonchalant flight behavior or not. Okay, so in general, the authors do find some really strong support in their results. So now let's strong support for their hypothesis here. So let's now turn to the discussion and see what some of the main take-home messages are. Okay, so did their results support their predictions? In general, yes. Very clearly, very strong data as represented here. They summarize it in the discussion by saying, in other words, moths with more potent chemical defenses are more likely to display nonchalant flight. It's a very bold statement because they had very bold data that showed this really well. Good job, guys. All right. They did have a couple of other findings that were interesting. They found that when they compared 2 of the species that do the most acoustics whenever they're approached by bats, that was B. trigona and C. arizonensis. Those 2 species do really high frequency, really bold sonar jamming sounds, hypothesized sonar jamming sounds. and so, again, we don't, in trying to understand what is the purpose of that sonar jamming, we look to see what the outcomes are and how that relates to palatability. And what the authors found is that these 2 species, which have similar levels of acoustic defense, show very different levels of nonchalance, and also correspondingly large differences in unpalatability. So here I've indicated with red arrows these 2 species. And remember, both of these species share the same acoustic defense relative to attacks by the bats. But they show very different levels of nonchalant flight behavior. The species on the right is more chemically defended, we infer from the bat feeding trials. Bats would only eat them a very small amount of the time, as represented there by the light gray bar. Most of the time, bats deem them to be unpalatable. So in addition to having their acoustic defense, they've also got the chemical defense to back that up. That is probably why, of course, that they exhibit nonchalant flight behavior much of the time, and only about 30% of the time do they try to evade bats. Whereas our species over here that is more palatable, we see that here, that it was eaten by the bats roughly 2/3 of the time, represented by the light gray bar here. And forgive the teleology again. This species knows that it is more tasty to bats, and so it is going to exhibit nonchalant flight less of the time, in this case only about 44% of the time. Okay, another interesting finding that the researchers had that came out of the study is a case of possible Batesian mimicry. This involves on the chart here. This involves the species on the far left and the one in the middle, both of which are in the same genus. Both exhibit nonchalant flight behavior, from one more than the other, but one is toxic and the other is very yummy. So even though the species on the far left is showing nonchalant flight behavior, perhaps to suggest to bats that it's toxic and it's not worth an attempt to eat. Instead, it is actually would be eaten by the bats about 4 out of 5 times. So this would be an example of Batesian mimicry, where one species is mimicking another, even though it doesn't have the same degree of chemical defenses to back up that signal it's sending with the mimicry. The authors do point out that more study is needed in order to figure this out and make sure that this is a case of Batesian mimicry. All right, so if we zoom out to the big picture and consider whether or not these authors found support for their hypothesis or not, I would say that, in my own opinion, that they did a very good job of finding that support. I'd say that they nailed it. All right, now let's turn to the broader significance of the study. And already we've talked about this when we're covering the introduction and the background information to the study, and that this study is one of the first, or they claim it is the first, to comparatively examine escape behaviors of aposematic insects in a natural context. That would be the arena trials, right? Instead of feeding moths to bats in cages and like in flight cages and things like that, they're actually testing wild bats that are free ranging and feeding them moths that were captured from the wild and then turned loose on the bats roughly a day later or so. So that was a first. They also they were the first paper to compare the likelihood of escape between both aposematic and mimetic species. So both the species that are exhibiting aposematism and also mimics. And then they were also the first to construct a predictive model of escape behavior. So a lot of firsts there for these authors. There's other aspects of the broader significance to consider. One is that they rightfully claim that this is a really good model from which to study predator-prey interactions. Both species can be worked with a controlled enough environment that you can get good data. So this is a good model system for looking at aposematic behavior, such as sluggishness, and signaling by the moths, such as the acoustic sounds that the moths make, and possibly the sluggish behavior if it's aposematic signaling. This is a good system to sort of tease out the very subtle relationships between these factors. It's also a good system in which they can examine the benefits of a behavior, in this case, flight behavior, evasive behavior, against the balance of the risk of death, figuring out where those curves cross. And I suspect that the authors have some other papers that are either been published or will be published that look specifically at that based on some of the things that they were measuring in this study. In terms of broader implications to things beyond these types of theoretical questions about predator-prey interactions, I'll leave it to you to think about, like, what are the more societal broader implications here. This paper obviously doesn't give any direct nod to those implications. They're all, of course, going to be very indirect, but I would still argue that there's some important things here of broader significance for the general public. All right, so that concludes this review of the paper and its discussion.